Now let's go back to our schematic yet again, and let's remove the stabilizing resistor, and I'll show you one last trick which makes it really easy to work out your stabilizing resistor. So let's just place a resistor in series with our base, with our input, and then we'll double click on it and we'll make it tunable. We'll give it a lower value of 0 and upper value of 60 in increments of 1 ohm, and click on OK. Now let's go back to our Smith chart and let's click on Simulate, and then let's open the tuner. Now what you can do, you know you've got a resistor in series with your input, and you want this resistor to be of such a value as to push the unstable part of your stability circles completely out of your Smith chart. So you can just start moving the slider until you actually achieve what you want. And you can see that for a value of 29 ohms, you've pushed the unstable part of your stability circles completely out of your Smith chart, and you worked out your resistor incredibly easily. This is a fantastic tool that Microwave Office offers, and you might as well use it to your advantage. Stability, however, comes at a price, because inserting resistors either in series or in shunt with your input and or output ports will mean that you will have to give up some of the gain of the transistor. So if we go back to the S parameter table, you can see that the gain of the transistor has gone down from 5.4 to about 4.2. So let's go back to our schematic and let's talk a little bit about what the best configuration is for your resistive stabilization. Usually, and particularly in the case of low noise amplifiers, you don't choose a stabilizing resistor which is in series with the input. And the reason for that is that that's going to make the noise figure a lot worse, and you want to try and eliminate or minimize all the sources of noise when you're designing low noise amplifiers. So in this case, we wouldn't really want to use this 29 ohm resistor in series with the input. So for example, we could decide to use a 110 ohm resistor in parallel with the output. So let's just remove this one, and then let's put a resistor in a shunt with the output of 110 ohms, and let's use the DC blocking capacitor to avoid this resistor affecting our bias. And let's simulate. Now if we go back to our S parameter table, you can see that the gain has gone down even further. So you started from 5.4, you went down to 4.2 with the stabilizing resistor in series with the input, and now that you've put a shunt resistor at the output, you've gone down to 3.9. But this is a necessary evil, because you really want to avoid a situation where your transistor starts oscillating and potentially burns out. And you also want to make sure that you can meet the specifications of your design and hence achieve the required performance in a stable way. Now, there is another way to achieve stability which doesn't entail the use of resistors in the way that we've just used them. So let's go back to our schematic and let's get rid of any resistive stabilization that we've done. And we've said that for an RF amplifier, resistive feedback is really bad because it really decreases the gain considerably. For example, if I put a resistor in series with my emitter here, I would then achieve some feedback and hence some stability, but I would give up an awful lot of gain. But what about putting an impedance in series with our emitter which is purely reactive, so one that has no resistive losses whatsoever, that might give us some feedback without making us give up quite as much gain as a resistor would put in the same position. Now, what kind of impedance can we put in there? Of course, if we want it to be purely reactive, it's got to be a capacitor or an inductor. It can't be a capacitor because a capacitor would be a DC open circuit and hence would not allow a bias current to flow through the transistor. So we need to use an inductor. We have no choice. So let's move our ground connection a bit further down. Let's get ourselves an inductor and place it in series with the emitter like so. Now, what value should this inductor have? Of course, it's going to give us some feedback, some reactive feedback at the frequency of interest, because the inductor is going to be a short-circuited DC, thereby not affecting the bias at all, but at the frequency of operation it will have a finite impedance which will then feed back between input and output and allow the transistor to be stable. Now let's start with a really small value, let's say 0.1 nanohenries, really tiny, and make this tunable. Then we'll go back to our Smith chart. Let's change it back to an impedance Smith chart to avoid confusion, and then simulate. Of course, our stability circles now are back inside the chart, as one would expect. Now let's open the tuner, and we've got the value of our inductor in the tuner. We can select the range to be between 0.1, let's say, and 1 nanohenries. And then let's start increasing the value of our inductor and see what happens. As you can see that as I increase the value of my inductor, I am pushing the stability circles out of my Smith chart, thereby ensuring that there are no unstable terminations on my chart. So as I keep increasing this, you can see that for about 0.8 nanohenries, both unstable parts of my input and output stability circles are completely outside the chart, and hence I've achieved unconditional stability, but of course only at the frequency of interest, which is 1900 MHz. So this gives you stabilization, but the stability refers to the frequency at which you're working at the moment. So let's close the tuner and let's have a look at our gain. We can see that the gain is pretty much around 3.9 again, so we are in a similar situation in terms of gain as we were when we used a shunt resistor to stabilize the transistor. So we haven't really lost much in terms of gain, but all we've got now is a tiny little inductor in series with our emitter. Its value is really quite small, and hence we could even realize this with some via holes from the emitter down to the ground plane of the transistor. That might be enough to actually give us the inductance that we need. So let's take away the tuning from our inductor and make it about 0.8 just to make it a fixed value. And then what we'd like to see is how the stability across a range of frequencies is affected when I'm using this particular type of matching. So first of all, let's have a look at frequencies which are higher than our frequency of operation and try to think what you think will happen to our stability if our frequency is higher than the one that we are at the moment. So we're going from 1.9 gigs to 4 gigs in a step on 0.1 gigahertz. Maybe we'll make a step at 0.3 gigahertz and then click on apply and then OK and simulate. Now let's have a look at our stability circles. You can see that our stability circles are still completely outside the Smith chart, and that's to be expected because of course our inductor is going to have a higher and higher impedance as I increase the frequency, and the more impedance this element has, the more feedback it provides, which means less gain and means more stability. In fact, if we go back to our S parameter table, now of course this is shown for different frequencies as well, and we look at the S21, you can see how S21 decreases as frequency increases. This is due to two things. First of all, the gain of the transistor decreases as frequency increases, but also we've got this inductor whose impedance increases with frequency, so we get an increased feedback and hence a reduction in gain. But what happens when we have frequencies which are lower than the frequency of operation? So let's go back to project options and then we'll start this time from 0.1 gigahertz. We'll go up to 1.9 and again we'll do this in steps of 0.3 gigs. Click on apply and then OK. Then let's go back to our Smith chart and click on simulate. And you can see that now all the circles have moved back into the Smith chart, and hence you have a number of unstable regions which would make the transistor unstable if the frequency of operation was lower than the one that we stabilized it for. And this is to be expected because the inductor will have a lower impedance, will provide less feedback, and hence we'll end up with a transistor which is potentially unstable. Now it is all well and good stabilizing a transistor for a specific frequency of operation, but you may end up having some stray signals that come in, or you could have a broadband operation, and hence you want to stabilize the transistor across a broader range of frequencies if possible. What we can do is add some stabilization, which only works for lower frequencies and does not affect the operation of our transistor at higher frequencies. So how do we achieve this? Well, let's go back to our circuit here, and yet again let's put a resistor in shunt with the output. And then of course we need to use a DC blocking capacitor in series with it to avoid it affecting the bias, and then add a ground connection on one side. Make it tunable and then click on simulate. Now let's go back to our Smith chart. We can see that we've got our stability circles which are still partially inside the Smith chart, and we don't want that. But we've got a 500 ohm resistor at the moment which is relatively high, and because it is in shunt with our output, it's not really taking away too much gain. So what we can do is open the tuner, and then we'll start decreasing the value of our shunt resistor, which means increasing the conductance, and this should push our stability circles further out, although of course it will also diminish our gain. So if we decrease its value, you can see that we're pushing the circles out, and then we get to a point where they're pretty much completely out of our Smith chart. So if we put a 250 ohm resistor in shunt with the output, this helps the stability, but it will of course also have an effect on the gain. So if we go back to our S parameter table, you can see that the gain in 1900 MHz now has gone down from 3.9 to 3.3, and that's not ideal. Can we recover that gain? Yes, we can. If we go back to our schematic, we can make this resistor completely inactive at the frequency at which we're operating, because we know that at that frequency our transistor is stable and we don't need any further stabilization. But equally we can make it active at frequencies which are lower than the frequency at which we're operating. And this can be done quite easily by adding an extra element in series with this branch, which is a quarter wave transformer. So let's press Ctrl L and pull up a till-lin element, thread a transmission line, which is 90 degrees in length at 900 MHz. So let's just remove this ground connection here, put this in series with our branch, and then add a ground connection at the end of it. Now, because this transmission line has got an electrical length of 90 degrees at 1900 MHz, this means that it's a quarter wave long at 1900 MHz. And as we've seen in the manual, that means that this will flip any impedance on the Smith chart by 180 degrees. So here we have a short circuit, and because this is a quarter wave long and 1900 MHz, this short circuit will appear as an open circuit here. So the high frequency signal will see a high impedance at this point here, ideally an open circuit, and hence there will be no RF power of 1900 MHz flowing down this branch and into ground, and hence we won't have any additional attenuation created by this 250 ohm resistor at the frequency of interest. But of course, when we are at a frequency which is lower than 1900, then this quarter wave transformer won't work anymore, and hence we will still have the stabilization that we crave. So let's click on simulate, and let's have a look at the stability circles first. And as you can see, we are pretty much there still. They are all outside the Smith chart. And then when we go and have a look at the S parameters, you can see that our gain at 1900 MHz has gone back to about 3.9. So we've regained the gain that we'd lost. But still, we have a circuit which allows us to have stable operation across a broad range of frequencies. The emitter degeneration implemented with a purely reactive element allows us to have feedback at 1900 MHz and higher frequencies, thereby giving us stability in that region. And then the 250 ohm resistor in shunt with the output gives us stability at lower frequencies. Now lastly, let's have a look at our mu factor and see how that has changed now that we stabilized our circuit. So let's go to project options and select a wide frequency range, say between 0.1 and 4 gigs in steps of 0.1 to gigahertz. Click on apply and then OK. Then simulate, and let's see the mu factor graph. You can see that now the mu factor is always above 1 for all frequencies, including the one that we are working at. So we've basically achieved unconditional stability across a broad range of frequencies, which is what we wanted to achieve. We can also create a copy of our schematic, and then we can take away the reactive feedback through emitter degeneration and go back to the initial configuration that we had with the 110 ohms shunt resistor at the output. And let's rename this schematic and call it as parameter measurement resistive stabilisation. And now what we can do is go back to the mu factor graph and add a new measurement, and this will be under the stability section, and it'll be mu1, and we'll look at the mu1 for the resistively stabilized circuit and see how it compares. Click on apply and then OK, then simulate. You can see that if you use resistive stabilization alone, then there is a region in the frequency band which is lower than your frequency of operation, where the transistor is potentially unstable, and that's certainly not a good thing. Could we do something about this? Well, usually the way to make the transistor more stable is to actually give up more gain. We could go back to our resistive stabilization schematic, and we can make the stabilizing resistor tunable. And more likely than not, if we decrease its value, which means giving up more gain, because of course we are putting a resistor in shunt of a lower value and hence letting more current flow through it and take away from the load. And if we go back to the mu factor graph, and then if we open the tuner and we decrease the value of our resistor, you can see that for lower values of resistance you can have unconditional stability even when you just use a purely resistive stabilization method. However, this will also mean decreasing the gain of the transistor, because now your shunt resistor is taking away more current from your load. So let's close the tuner and go back to our S parameter table. So if we right click on this chart and go to add a new measurement, choose S parameters and choose S21 coming from our resistively stabilized schematic, click on apply and then OK, and then we simulate. You can see that at the frequency of interest, which is 1900 MHz, whereas you have a gain of about 3.9 for the circuit that uses reactive emitter degeneration, you have a lower gain of about 3.6 for the resistively stabilized circuit. Of course, we can change these values into dBs if we want to. That could provide a better comparison, and you can just do that by right-clicking, going on to Properties, and then choose dB magnitude and angle, and clicking on OK. So then you can see that at 1900 MHz for the reactive emitter degeneration arrangement you have 11.8 dB of gain, and for the resistively stabilized circuit you have 11.1. Now let's revert back to having these values in terms of magnitude and angle. Click on OK, and then in the next tutorial we'll be looking at how we can maximize the gain and the performance of our transistor by using the appropriate matching networks at the input and output terminals.